So compounds display constant composition. Most of the things that we see in our everyday lives are not elements, they are compounds. Free elements are actually relatively rare in nature. Compounds are formed from elements that are combined in fixed, definite proportions. I should get out my highlighter, perhaps. Fixed, definite proportions. That's different from a mixture. In a mixture, the composition can vary. If you put sugar in a cup of tea, you can put a little bit of sugar, you can put a lot of sugar. But if you're making the sugar molecule, the compound, it has to have a particular number of carbon, hydrogen, and oxygen atoms. And it's always the same. So here we're looking at a mixture versus the compound. So this balloon is full of hydrogen and oxygen, the elements. Those are the components that make up water. But this balloon, if you light a match and bring it and touch it, it'll go kaboom, because hydrogen and oxygen are very flammable. This balloon, it actually, the first time I saw this picture, I'm like, what on earth is that, right? That is a very well done picture of a water balloon popping. So the balloon is just pulling away from the water and the water hasn't fallen yet. It's kind of a cool picture. Balloon full of water also contains hydrogen and oxygen, but they are bound together in this particular form. They look like little Mickey Mouse heads to me. 2 hydrogens to 1 oxygen. There is a definite composition. The ratio of hydrogen to oxygen is always the same. In a mixture, you could have a little bit of hydrogen, you could have a lot of hydrogen, okay? This idea was formally stated by Joseph Proust back around 1800. This idea, and this is called the law of constant composition. All samples of a given compound have the same proportion of their constituent elements. This means that there is absolutely no difference between, say, vitamin C that is isolated from a plant and vitamin C that is made in a chemical lab. They are exactly the same. We can look at mass ratio. If we take a sample of water, say an 18-gram sample of water, and we decompose it into its elements, hydrogen and oxygen, you would get 16 grams of oxygen, 2 grams of hydrogen. It has a mass ratio, oxygen to hydrogen, of 16 to 2, or which is equal to 8. We would express that as a ratio as 8 to 1. Any sample of water, pure water, is going to be 8 to 1 oxygen to hydrogen by mass. Doesn't matter where the water came from. So let's look at this example. 2 samples of carbon monoxide from different sources decomposed. One sample produces 4.3 grams of oxygen, 3.2 grams of carbon. The other sample produces 7.5 grams of oxygen and 5.6 grams of carbon. Are these results consistent with the law of constant composition? The law of constant composition says the ratio of the masses of elements in a compound has to be the same. And so we can analyze this by looking at the ratio. So because there's more of the oxygen and less of the carbon, let's do oxygen to carbon. So for that first one, it's 4.3 grams of oxygen to 3.2 grams of carbon. I was going to get my calculator out, and then I forgot. No, I don't want that one. So 4.3 divided by 3.2, bless you, gives us 1.3. So a ratio of 1.3 to 1. And then we'll take the numbers for the other one. We'll do oxygen to carbon again, 7.5 grams of oxygen to 5.6 grams of carbon. 7.5 divided by 5.6 also equals 1.3. The ratio of the mass of oxygen to the mass of carbon is the same for both samples of carbon monoxide. Is that consistent with the law of constant composition? Yes, it is. Any questions?